This is lecture number 30 of the course ME314 Fluid Mechanics 2, and this is the third lecture of this week. We're talking about boundary layer, order analysis, and in the last class we have done the Glacier solution. That is when the laminar flow takes place over a flat plate, and we end up with the expression for boundary layer thickness, wall shear stress, and friction coefficients. Today we will talk about the turbulent flow, and we will see how the governor equations of the turbulent flow would be, and then we will end up with this the concept of boundary layer in the turbulent flow, and we will look into the different velocity profile comparison of the velocity profile for laminar and turbulent flow. And in the end, we will be interested in more closely the velocity distribution close to the wall in the turbulent boundary layer, and in the end, we will do this law of wall. Okay, so as we know, the turbulent flow is characterized by chaotic and unsteady flow motion, which is producing disorder. So, in contrast, in laminar, it is the streamlines are in ordered. And obviously there are some eddies formation takes place, so there is a verticity associated in turbulent flow, and due to that a high momentum transfer in the advection phase, so there would be a better mixing in turbulent flow. When you look at the velocity variation with time, so we know that let's say this u is the velocity component, instantaneous velocity component in the boundary layer region. So there is an average time average of the velocity component. We call it u bar, and the fluctuating component is actually u prime. So the velocity is varying randomly throughout the time as the time progresses. Similarly, the y component, which is v, has been varying, and there is some average of the v component, and there is a fluctuation component associated in the direction normal to the surface. So horizontal direction is parallel to the surface of the flat plate, and perpendicular to the surface is the y direction. So here it is shown into the depth, the variation of the velocity. As we already know from the instantaneous component of the velocity is actually which is a time dependent unsteady type. So what we do is we divide this velocity component into a time average component, which is u bar, which is not a function of time, and there is a fluctuating component of the velocity, which is a function of time. So the variables would be divided into two halves: the time average component and the fluctuating component for every instantaneous parameter. When we see this instantaneous values, we know that as in x direction, the velocity component is u, and its average is u prime, and its fluctuating component is u prime is the fluctuating component, and u bar is the time average component, and we are representing the averaging procedure by representing it with the bar that denotes the average component. So same thing, same composition, same decomposition rather, can be done with the velocity component v, and in two-dimensional space if we are dealing with another variable, pressure, because as you know, we are dealing with u, v, and pressure are the variables of interest we have in the space x, y, and t. So what we see here is that the concept of time averaging of the, let's say, the u component of the velocity could be whatever the variation of u taking place over the time period. You just integrated it, so it means you know the area under the curve, and you divide by the time delta t, which is fairly large enough time to capture the variation of velocity in that delta t interval. So this is our definition of the time averaging, where this delta t is a small interval, which is, but still it is large enough to record the fluctuations that has been taking place in this turbulent motion. So let's say we do the time averaging of that velocity. So what I know is this is an instantaneous component of the velocity which is varying with time t. So I have just substituted the velocity component u, which is a combination of time average component plus the fluctuating component. So I need to integrate that expression. So first both terms are separated out, and as we know, this is the time average term and this is the fluctuating component of the velocity. So if this fluctuating component is as we know that it is not changing instantaneously, but so area under the curve would be nothing, just u bar, and taking the upper limit minus the lower limit cancels out, you will get delta t. So delta t and delta t cancels out on this left hand side term, and this is the fluctuating part. So what we see is this is the time average, and this is once again the time average. So from that equation, this u and u cancels out. So what we end up with the process that the time average of the fluctuating part comes out to be 0. So whenever we are dealing with the fluctuating part, average of the fluctuating part, so this is by definition the average of the fluctuating part. Average is taken in a manner that first take the sum and divide by the total interval, we will get the average. So average of the all the fluctuating terms would be come out to be 0. So this important result we can apply it to any component of the velocity. We have taken example of u component of the velocity. So we have an average is here represented by the bar here. So the average of the fluctuating comes out to be 0 here. So similarly, we can say the same thing about the fluctuating component of the y component of the velocity, as well as the fluctuating component of the p is the pressure, which is instantaneous pressure having a distribution of the time average pressure plus the fluctuating part. So but the point is, once we take the product of the two fluctuating components, we are not going to get 0. So the average time average of the fluctuating component is 0. But if u prime and v prime both are instantaneous components, then their time average is not 0. It is a non-zero term, which is actually, it means there is if you take the product of the two fluctuating components and take the average, it will be a non-zero value. Okay, now let's see, go into the governing equations. For simplicity, what we have done is we have taken 2D incompressible constant property fluid, in which our continuity equation would be a steady flow as well. So our continuity equation in instantaneous velocity component would be, I have just substituted instead of u, just substituted instantaneous velocity component u and v. So here, as I know that u is a combination of time average plus the fluctuating part, so I have just substituted here, and then we simplify. So as we know, if you take these two components, these fluctuating components, their average comes out to be 0. So the fluctuating components, average of the fluctuating components of the time average of the fluctuating components are 0. So what we end up with the same continuity equations. Instead of instantaneous velocity, now you are having the same governing equations, but with time average component of the velocities are present. Same thing. So what we see is in turbulent flow, the time average velocity components satisfy the same governing equations which satisfied for laminar flow. So what we have just replaced, the instantaneous velocity component is replaced with the time average velocity components, which are so the time average of the fluctuating is 0, so you end up with that equation, which is exactly the same as the continuity equations for laminar flow. So only difference is in turbulent flow we are dealing with the time average of the velocity. Same thing can be done with the x momentum equation. So we have inertial term here, and we are ignoring the gravity. So this is the pressure gradient term, and this is the viscous term. So we have only included the y component of the velocity because we are dealing with the boundary layer. So this would be substituting the instantaneous component, all these values to be substituted in that x momentum equation. And once we substituted everything and simplify, we are not going into the process of cancelling out. But what we will end up with, we will end up with the same scenario, having inertial term, having the pressure gradient term, and having the viscous terms. But in viscous terms, interestingly, we do not have this just the time average of the velocity, but once you take the product, then there is another viscous term is involved, that is actually the non-zero term due to the product of the fluctuating component of the velocities. And if you take the time average, that will contribute into the viscous term. So we call that to be our, this is our laminar stress term, and this would be called as turbulent stress term. So this result shows that the inertial term is same, the pressure gradient term is same. Instead of instantaneous pressures, we are only dealing with the time average value of the pressure and the velocity. So the viscous term having two components, one is contributing for the laminar part, and other is dealing with this turbulent part. So we just call it that part to be the this part is actually called as laminar part, which is L is the superscript L is representing laminar, tau is the shear stress. So shear stress would be exactly the same as you know from your Newton's law of viscosity, that mu times how the velocity gradient changes in the y. We call that to be the viscous shear stress. Laminar viscous shear stress. So and then this part is actually called as turbulent shear stress. So interestingly, this turbulent shear stress is something which is not known, and the study related with involving this turbulent shear stress, there are different models that are present to represent the turbulent stress. For example, Prandtl mixing length model or different turbulence models, which allows us to calculate that unknown term of this turbulent shear stress. So this is something beyond the scope of this course, so we are not going into those turbulence modeling part, but we know that in turbulent flow the governing equations are like this, and the viscous term is having the laminar part as well as the turbulent shear stress part. Okay, now look into this. Already know that if u is the velocity component, and this is the variation of the velocity in the y direction. So if you take a cross section, in laminar flow, the molecular transport is low, whereas no, I'm sorry, this in laminar flow the diffusion is takes place not at the bulk level. It is taking place at the microscopic level. So where they have very high momentum, diffusion takes place, and diffusion is at the molecular level. So there is a random motion of the molecules, and they are moving very fast. And if you see one of the cross section, the plane A is a cross section. So here at section 2, the velocity is u2, and here the section 1, the velocity is v1. As we know, there is a certain velocity profile. So at section 2, the velocity is bigger than the velocity at 1. So u2 is greater than u1. So streamlines are parallel, and at a molecular level they are moving much faster. There is a random motion associated, but at the bulk level there is no momentum transfer, or we call it, that bulk level is called the advection level. So at the advection level, the momentum transfer is not taking place. In contrast to the turbulent flow, what happens is their diffusion is low, but their advection at a bulk level, they transfer momentum quite high, and here their velocity component is the time average velocity component, and the velocity profile is actually the time average velocity profile. So here there is a random chaotic motion, and in turbulent flow, because in laminar flow the stress is present between the layers of the fluid, so the friction present between the layers of the fluid. Here the friction is caused not just the layers between the fluid, because layers are not present, so their eddies are present. So what happens is these turbulent stresses is due to the three-dimensional chaotic motion of those eddies. If we see the motion over a flat plate, so this is a flat plate in the direction of x. We call it an horizontal length of the plate in the direction of x, and normal to the plate is y direction. So once this is our leading edge of the flat plate, so initially there is no disturbance in the flow in the within the boundary layer, where the viscous effects are dominant and the velocity gradient are present. And we know the outside the boundary layer, the velocity is nothing, just the free stream velocity u infinity we have mentioned here. So, but within the boundary layer, there is a velocity gradient exists. So, the velocity is varying in the direction of y. As you are moving in the y direction, because when your y is 0, your velocity is 0. As you are moving in the y direction, there is the velocity change takes place. So, velocity is increasing as you are moving in the y direction. After certain length, what happens is there is a burst, first burst is started, and there is some fluctuation takes place in the layers of the fluid, and so we call that to be the transitional region. And once this transition occurs, and the boundary layer thickness is actually fluctuating with the time as well, and along this space as well. But after certain distance, what we call it, once the transition region is over, then the whole flow becomes turbulent, which is composed of eddies. But only the layer which is very much close to the wall would be still the viscous sublayer. We call that layer to be viscous sublayer, and we will define it in this later part of this lecture. So this would be the typical distribution. So, but this diagram is just a schematic representation of the boundary layer in laminar region, transition region, and the turbulent region. And that is characterized by the Reynolds number. We will talk about later, but we know that this boundary layer thickness, the vertical distance from the plate where the local velocity is approaching towards the free stream velocity, so that distance is actually the boundary layer thickness, and we represent by the delta, which is growing as we are moving in the direction x. If we draw the same thing on the scale, and we see that this is x is the length, horizontal direction, y is the vertical direction. So this vertical distance is very much smaller than the horizontal distance. And if you see, the laminar region here is almost non-existence, and I mean it's something very small region to which the flow is laminar, and then you have a large length over which there is a transition takes place, and after certain length this transition turns into fully turbulent flow. So and the boundary layer thickness is very thin in this laminar region, so even it is not being shown here, and slightly visible in transitional region and the turbulent region. So in practice, after a long distance, this transition takes place, and in order to get rid of this long distance, sometimes in experiments, what we do is we put a trip wire so that we initiate instability in the flow, so that this transition region gets shrink down, and we can measure the thicknesses or some parameters of interest in the experiment in a shorter length. So this diagram actually shows that actual scales are much smaller than this representation, which is just a schematic representation to show, okay, this much is the thickness of the boundary layer, but in reality it is this very small distance, almost non-visible in this actual measurement. It is much smaller, very much small fraction of that, very small fraction of that. So okay, now we classify this laminar region under which the streamlines are parallel and there is no disorder, there is no chaotic motion, there is no verticity associated. Then this distance is called the critical, xc would be our critical distance, and critical distance in x direction. And after that there is some transition region, and then the turbulent region starts. So what we call it, once we have a flat plate over which the flow is such that there is zero pressure gradient, so we are not talking about pressure gradient term. So there is a zero pressure gradient, then this typical value of the Reynolds number at which this transition takes place is if Reynolds number approaches to the 3 into 10 to the power 5 this number, because it's a dimensionless number. So it is actually the characteristics of the flow in such a manner that rho and mu are the fluid properties, and x is the distance, which is your characteristic length, and u infinity is the characteristic velocity. So Reynolds number is a combination of the material properties, the characteristic velocity and characteristic length. So it takes care of both the inertial and the viscous forces, and we know that this critical Reynolds number over the flat plate is 3 into 10 to the power 5. And you know from your FM1 knowledge that in the pipe flow cases, the critical Reynolds number is order of 2000. So if it is less than 2000, it will be called as laminar, and if it is greater than 2000 to 4000, it is a transition region, and turbulence started with 4000, and then once the Reynolds number reaches 10,000, then it is fully turbulent flow. That was the case in the pipe flow. But right now we are talking about the flat plate, so the critical Reynolds number are much bigger in the flat plate. So if the flow over is taking place for a rough plate, so rough plate is having crest and trough. So what will happen is or even if it is a smooth plate, but your free stream velocity is having certain fluctuation intensity, so it means u infinity is not just without disturbance, but if it has some disturbance in the free stream flow, then we can see that the critical Reynolds number can approach to something 5 into 10 to the power 5. So this is not just sometimes 1 into 10 to the power 5, sometimes 3 into 10 to the power 5, sometimes 5 into 10 to the power 5. So it all depends upon the condition to which the free stream is having fluctuations or not, or the condition of the flat plate, whether you have a blunt edge or you have a sharp edge. So in this diagram you see the flat plate is having a very sharp edge. So if there is a blunt edge, then the critical Reynolds number would be some different value. So it varies from experiment to experiment and from condition to condition. But these are some typical values. And if we have extremely low fluctuations in the free stream velocity, that the case in the research labs where laminar flow would still be present, even your Reynolds number reaches up to 10 to the power 6. So this number is depending upon the given condition. We know this boundary layer thickness is actually typically is we don't know exactly what is this vertical distance is, but we arbitrarily defined arbitrarily means we are fixing by our own. So it is actually the path to which the velocity, local velocity, approaches towards the free stream velocity, or sometimes we call it 99% of the free velocity. Then this thickness would be the boundary layer thickness. Okay, so the question is where this boundary layer thickness is actually exists. So the edge of the boundary layer thickness cannot be observed in an actual flow. So if you look at the picture of that actual flow in turbulent flow, then we see that at some point the boundary layer is small, some point it is high. So there is something fluctuating in this stream-wise direction. So we cannot actually exactly knowing, for example, at some point of time, instantaneous boundary layer thickness, because it is some point, it is zero point 0.4 of the arbitrarily taken delta. And so this is something that line is drawn is actually just arbitrarily drawn by taking the average from this distance is varying from 0.4 delta to 1.2 delta. Sometimes you have higher to that delta, sometimes you have smaller to that delta. So keep in mind in turbulent flow, due to this chaotic motion, this delta thickness, boundary layer thickness is do not have any sharp boundary. So that is changes with the time. So what we do is we take the we need to take the time averaging. So here you see this velocity profile is drawn as a time average velocity profile, and this thickness is actually we call it a time average thickness. So it is, but if you see in reality in actual flow, there would be some smaller thickness somewhere you have a bigger thickness than this time average thickness. So just like the instantaneous velocity idea, the same goes with the thickness as well. And there is a small thickness, what you call it, a viscous sublayer, which is very much close to the wall. Delta V we have represented here. So delta V is just a viscous sublayer. Even in the turbulent flow, that layer is having no disorder. So that would be very much close to the wall, very close to the wall. That is not shown on the scale, but just an exaggeration that is shown on this schematic. And and what we see here is the time average velocity profile is different from the laminar profile. So the two gradients are different. And if we see that so the boundary layer thickness varies with the time. So the actual edge of the boundary layer thickness cannot be predicted. So this is actually the time average thickness, and the resulting profile would also be a time average velocity profile. Turbulent flow, if you see the how this is actually the magnitude of the velocity u bar y for turbulent flow, with the same y with the same thickness, the velocity is much higher than the laminar case. So, in reality, as we know that the variation of velocity is if u is the instantaneous velocity, so it is actually the varying in the y direction. So due to this turbulent nature, and this blue line is actually represent the time average of that velocity component, which varies with the y. So u bar y means the how the time average velocity component is varying. And there is a marked difference here between the laminar profile and the turbulent profile. And this turbulent profile has a greater slope at the wall compared with the laminar flow. And this viscous sublayer is very much close to the wall even in this turbulent flow. And we will see it later how different types of zones are present in this turbulent boundary layer. So we know the process of eddy formation in this turbulent boundary layer. In laminar, we do not have vorticities, but once vorticity starts developing, and in this turbulent region, the mixing takes place due to that advection of those eddies, which transfer momentum from different layers in a chaotic manner. And the flow is dictated by the time average velocity component in turbulent boundary layers. So if you see the flow in this laminar region very much close to the wall, what you call it a just viscous sublayer, even the velocity profile, the wall shear stress at the wall would be mu times how the u changes in the direction of y. So and we can write down this separate the variables u and y onto the other side, and wall shear stress and dynamic viscosity is in this part. And if you integrate that separate after separating the variable, you integrate that, so this time average velocity component would be mu wall shear stress over viscosity times the vertical distance y. And we can simplify that expression just by writing down the same expression tau w, which is a wall shear stress over viscosity, and here just multiply and divide by the density. So here we know that mu over density is the kinematic viscosity, and one of the density is here in this denominator. So this density in this numerator is brought to the denominator. It would be mu over rho, and mu over rho is actually nu. So this would be our formula for and here, as we know, our time average velocity is tau divided by density divided by kinematic viscosity. So from this equation, what we have done is if you multiply together, it would be the same equation. So just bring these two things in the square root. If you multiply together, it is actually without any square root. So this equation can be written, the term in this square root can be defined as some fictitious velocity, what we call it a shear velocity or friction velocity, because the units for wall shear stress and density, and if you take the square root, you get the units of velocity. So this term in this square root is represented by a letter u tau, which is called the shear or the friction velocity. So that equation can be written as this is the time average velocity component, and this is the fictitious velocity. So this becomes a dimensionless velocity, and this dimensionless velocity is a function of a parameter called y times u tau times divided by kinematic viscosity. This time average component in this velocity boundary layer can be divided into two distinct regions. We call it an inner region and an outer region. So in this turbulent boundary layer, when your eddies are present, so from this distance to this distance, we call it inner layer. And inner layer is having three distinct layers like sublayer, buffer layer, and fully turbulent layer or a log region. So if this inner layer is composed of three distinct zones, and above the inner layer we have an outer layer. So we see in this sub layer there is no the flow is laminar in this viscous sublayer, and in this buffer layer some burst of eddies starts forming, and in this turbulent region we have a significant amount of eddies are present in that, and the same eddies are present in this outer layer region, but the velocity is approaching towards the edge of the boundary layer is the thickness of the boundary layer, which is we know that it is a time average boundary layer thickness. It's not the actual thickness, but arbitrarily we assume that once your local velocity is approaching the free stream velocity, that is 0.99, then this would be the corresponding boundary layer thickness. So these three regions we can the velocity profiles in that three region can be studied, and we learn from the experiments that this dimensionless velocity, the instantaneous velocity, time average velocity, and this friction velocity, this ratio is a dimensionless velocity, would be a function of vertical distance y times the friction velocity divided by kinematic viscosity. So this dimensionless ratio of velocity is actually a function of one variable, which is looks like the product of y times u tau divided by kinematic viscosity. So this dimensionless velocity becomes a function of one single independent variable. And the term here is also having since this is a ratio on the right hand side, is also a ratio, so this term is also a dimensionless quantity. If you compare the velocity profile in the laminar region, so here we have local velocity versus the free stream velocity. So once you are at the range of the boundary layer, then u would be approaching towards u infinity, then u over u infinity approaches towards 1, and this parameter, which is y times under root Reynolds number over x, would be plotted on the y-axis. So this is actually, if you write down the local value of the Reynolds number, it would be a parameter like having the same thing as velocity times the characteristic length and divided by the kinematic viscosity. It is actually the definition of the Reynolds number. So this would be the typical velocity profile once your flow is laminar, and in the bottom it is actual diagram of velocity is shown. So this is a flat plate, and you see the velocity profile, it looks like this, and close to the wall there is a boundary layer is generated, and as we are moving along the length of the flat plate, the thickness of the boundary layer thickness grows. In comparison, if you look at the turbulent flows, so at the close to the wall, their eddies are placed. So here we have time average velocity compared with the, instead of free velocity, we compared it with the u tau, which is the friction velocity. And if it is plotted versus this dimensionless parameter, which is exactly have the same feature as this term y under root Reynolds x over x, so it is exactly the same. So this is not a continuous curve from 400 to, this is a discontinuity, the 500 is not here, so just to show that there is a longer length here. So this is the velocity profile, and we see close to the wall at this when this distance is 1 or this is 100. So actually the velocity, this part is much greater than this laminar part. So if we look at more closely this curve, so there is in the vertical distance, actually instead of vertical distance, if we plot this dimensionless parameter y times u tau over nu, which is a dimensionless number, in the horizontal axis you also have a dimensionless velocity. So we see this laminar sublayer is very much close to the wall, and then we have a buffer layer And then we have a log layer, what you call it, where the core is in turbulent, and so this length is representing the inner layer. When this parameter equal to in the order of 500, then this is the vertical distance, what you call it, an inner length. And other than greater than, when this number is greater than 500, it would be the outer layer. So, if you see the flow completely, or what we have done is just toppled the quantities in the horizontal axis. If you have dimensionless velocity, now in the vertical axis you have a dimensionless velocity. So if you plot the overall flow, then obviously at your local velocity, time average velocity would be approaching towards the free stream velocity, then this distance would be equal to your delta. So when y over delta approaches 1, it means your y equal to delta. It means you approach towards the boundary layer thickness. So that would be the typical velocity profile. And keep in mind the shape is different just because we have switched the variables. Here this vertical distance, dimensionless distance is plotted, and here the velocity profile is plotted. And due to this log nature of this velocity distribution, what we need is we need to define this outer region. Instead of dimensionless velocity, we just represent as the difference between the local velocity and the free stream velocity divided by this friction velocity, or so that would be called, this difference is called as a velocity defect. So our outer layer region can be represented as a simple function of y over delta in the outer region, which is close to, so that would be a simple function of y over delta. And this difference of velocity is actually called as velocity defect. And sometimes this quantity, this dimensionless number u over u tau is represented as u plus. So u plus is another variable which is nothing, just a dimensionless velocity, which is the time average velocity over this friction velocity. And similarly, this y distance, this distance is u times y times u tau over nu is another vertical distance. We call it a dimensionless distance in y, and this distance is represented as y plus. So instead of writing down this whole thing, we can simply write down y plus. So what we do is, this inner region we divide into three distinct zones, what you call it. The first one is called the viscous sublayer, which is very much close to the wall, and then you have a buffer layer, and then you have a turbulent zone. And from this turbulent zone, these three layers are called in the inner region. And there is an outer region, and there is an overlapping portion between inner and outer region. But because of the nature that there is the same straight line behavior is in this outer region, and there is some mathematical equation which represent that behavior. So whole turbulent flow in the boundary layer region can be divided into three distinct zones. First one is very much close to the wall, is called viscous viscous sublayer, and then you have a buffer zone, and then the turbulent zone. As we know that molecular level, there is a lot of diffusion takes place in the laminar boundary layer. So the same idea is there. You have highly fluctuating viscous wall layer, and here it is this is something strong function of this y plus value. So u plus is some strong function of y plus in that viscous wall region. And if you see that viscous wall region, that your y plus value, because this term is a y plus value, is something less than 5. So 5 is here. So here this u over u tau varies by some factor, and so this value, this region is being depicted with when your y plus is less than 5. And if your y plus changes from something like 50 to when your something y over delta is 0.15, something like that, in that region, when y over delta is order of 0.15, this region is called as logarithmic region. So in the viscous wall region, the velocity profile follows that relation, and in the log layer region, which is represented by that equation, that is in this turbulent zone, which there is some portion of that log law is in this buffer layer as well as some part is in the outer region as well. And we know that outer region, the velocity ratio, dimensionless velocity, is a function of y over delta, and in the inner region, the dimensionless velocity is a function of this parameter called y plus. In this logarithmic profile, this turbulent zone, what you call it, the y plus is somewhat greater than 50. 50 is somewhere here. So from 50 to when your y over delta is less than 0.5, the profile follows that equation. So this is what we have learned through an experiment over the flat plate, that this equation is fitted so that we can have the velocity distribution represented by that equation having 2.44 times of natural log of this y plus value plus some constant. The location, as we know, the outer edge is some strong function of the Reynolds number. As we know that in the viscous layer, it is a strong viscous layer is depending on that, and in the turbulent zone, it is also a function of this number, which is having some Reynolds number. So as Reynolds number increases, this straight line behavior changes. So at higher Reynolds number, you're going into this side. When smaller Reynolds number, you are going to this side. And since this buffer layer is at sort of the profile of the logarithmic layer and the viscous layer are both are present in this buffer zone. So in that there is no velocity profile is specified. So we specified the viscous sublayer and we specified this turbulent zone that is represented by this logarithmic profile. In the outer region, we already have learned that the velocity defect, which is critical, and the ratio of the velocity defect over the friction velocity is a function of y over delta. So when your y over delta is 0.15, so it is something, this equation is followed, and when your y over delta approach from 0.15 to 1, and then this equation is followed, and this velocity defect have this because this negative number is representing this negative slope here. So in this outer region, a logarithmic profile in this some part is of that is in the inner region, and some is in the outer region. So there is when your y plus is greater than 50 and y over delta is less than 0.5, so you are in this logarithmic profile region. And when your y over delta is greater than 0.15, then another equation is best fitted on this representation of this velocity profile, which is shown with this ratio dimensionless velocity defect over that friction velocity. And what people have done, they have performed experiments, and different people have different experiments. So as we know, the viscous sublayer is when your u plus is same as the y plus, so you have that profile, and on this horizontal axis you have y plus value and u plus is plotted on the y axis. So different people have done different. For example, in the log law region, we know that there is some constant, and kappa is 1 upon kappa is a constant, some constant here. So the velocity profile in this log law region, which is represented by this green line, which is a log law region. So there is some overlapping part with the viscous sublayer as well as with the buffer zone, and then this red line is following that law. And then the same this line, which is the purple one, is following the 1 upon 7 power law, where the time average velocity with the free stream velocity, this ratio is function of y over delta and some power of 1 by 7 power. So that is actually called as 1 upon 7 power law, and which is very much the same as uh, the experiments are. So these circles are the data that has been plotted through experiment, and the lines are following that mathematical equations. No? So there are different experiments performed. For example, this one is a black one, is a line which follows by very much follows the experimental part, that is called as Wall-Weak law, which is some mathematical equation. And most recently, this Spalding, which is following that law, having a mathematical relation, looks like this, where you have the velocity distribution. So in the turbulent boundary layer, the velocity distribution is represented by these laws, and since they are very much close to the wall, that's why these laws are known as law of walls. And in CFD study, it is not possible to draw the nodes very much close to the wall, so these mathematical relations help us to depict the velocity profile. So they are called as some wall functions in those CFD simulations. So I think here we stop today's lecture, that we know how the velocity profile varying within this boundary layer in this turbulent, having distinct inner region and outer region, and the very much close to the wall is a viscous sublayer region, then the buffer region, and then inner region, and then an outer region. And different law of wall are taking care of the variations of velocity taking place in the this is the velocity variations, and this is the wall distances, dimensionless wall distances. So this is how we visualize the or calculate the velocity profile in the turbulent boundary layer regions. And the same treatment goes with different coefficients, different constants with the internal flow, because we have right now we have dealt with external flow problem, but the same treatment is required for turbulent flow in the internal flow problems as well.